Hello, everyone. It is my very large pleasure to introduce Michael DeBellevue, University of Nebraska-Lincoln, who will tell us about graded deviations, rigidity, and Koszulness. Michael.
I needed to change my pen color. All right. So just real quick, some notation before I get started, some conventions. So for the duration of this talk, K will be a field, and I'm going to be looking at rings R that are a quotient of a polynomial ring by a homogeneous ideal. Typically, R will be standard graded, so all of the degrees of the xi's will be 1, but this will not always necessarily be the case. So this will be a graded K algebra. And in this talk, I'm going to first talk a little bit about Koszulness, deviations, and regularity. And then I'm going to talk about what the vanishing of deviations means for the complete intersection in Koszul properties. And finally, I will talk about the rigidity of graded deviations. So first off, I want to talk about what deviations are. So there's this theorem that Scholler proved back in 67 and Gullikson proved in 68. Pretty much independently using different methods, but they proved that for R, K, a local ring, they were really only concerned with the local side. The minimal resolution of K over R has the structure of a differential graded algebra resolution, which I will abbreviate as DG, differential graded algebra resolution. And this is oftentimes denoted in the literature, completely suppressing all kinds of information that you would ever possibly hope to have for a resolution. There's no indication of what the differential is at all or anything of the sort, but it's commonly denoted R Langle X Wrangle. And this is for a graded set of variables. And the grading on the variables just tells you the homological degree that they are joined in, and then the powers of those variables have homological degrees obeying the standard properties of a degree function that you would expect for an algebra to satisfy. And some important examples is when R is regular. This is just the ordinary Koszul complex. You just adjoin variables in degree 1 and nothing else. And another important example is Koszul complex. Another important example is when R is a complete intersection, in which case we, of course, do not have a resolution of the residue field by the Koszul complex. We need to do a little bit more, but instead the choice of X here, it's going to be 2 sets of variables, one in degree 1, one in degree 2. This is a generalization of the standard hypersurface resolution, in which case X2 would just be like a single element corresponding to that relation that you modded out by to make the complete intersection. Now, this really was mostly done for the graded, the non-graded side of things, the local side of things. But if you are interested in graded rings, you can essentially follow all of the same constructions identically, and everything works. And in fact, you get a little bit more. If R is graded, then you can furthermore assign a degree to each of the variables in this algebra resolution. Appropriately chosen degree, appropriately chosen internal degree yields not just any resolution, but a graded resolution, graded free resolution of the residue field with a set of bi-graded variables, with sets of bi-graded variables. And you can pick one out for each homological degree and each internal degree. So this whole thing breaks up into like an infinite union. And you really could do this with any grading, but I'm just going to be focusing on the standard in grading. So these sets of bi-graded variables are the sets of variables with homological degree I and internal degree j. This is how I'll denote them. The vertical bars and with a j, or excuse me, degree, the degree function. And this is how the deviations may be defined. The deviations are nothing more than the sizes of these sets. Deviations are just the number of the variables adjoined in homological degree I and an internal degree j. You can, of course, recover the ordinary deviations, the ungraded deviations, by just adding all of the graded pieces together. These are the ungraded deviations. And this is like what you would get if you localized with a homogeneous maximal ideal and then did everything in the local case. And just forgot about all of your gradings. And one of the reasons that deviations are of interest is because there's strong correspondence between the values, the numerical values of these deviations, and various ring theoretic properties. So some facts. Well, the first deviation, you're always going to start off with the Koszul complex on the very first set of variables. And so that's really just picking out the number of algebra generators of your graded K algebra R. So if you analyze them in each degree, in the jth internal degree, this is going to be the number of algebra generators, algebra gens of degree j. And the second deviation, we already saw an example of this. The Koszul complex is going to be exact if and only if the ring is regular. And if the Koszul complex is exact, then you would join no more variables in building this resolution. So this happens if and only if R is regular. And the third deviation is equal to 0 if and only if R is a complete intersection. This is all standard stuff coming from the local case, these two facts, but less well-known fact, but it's nevertheless true, is that there is relationship between the vanishing of these deviations off the diagonal. So now we have a graded structure that we can work with. We don't need to just think about vanishing of this whole thing. We can ask for vanishing in particular degrees. And in particular, I can ask for this off diagonal vanishing to happen. This is what I mean by off diagonal vanishing. I mean that this deviation is going to vanish whenever I is not equal to j. That's what I mean, because the diagonal would be like epsilon sub I. That's the idea here. So you vanish everywhere but on that diagonal. Well, this actually happens if and only if K has a linear free resolution over R. And this is just coming from the fact that in that resolution, R Langle X wrangle, basis of the ith homological degree piece is the set of all monomials of homological degree I. And so if each degree of a variable matches the homological degree of that variable, then the same will be true for every monomial, every product of those variables. So this property is otherwise known as being Koszul. Sorry, there's a train in the background, which I'm sure that you can all hear. I recently got a house which unfortunately is right next to all of the train tracks, but it's otherwise very nice. Hopefully it will not toot its horn that much more. An example of what I mean by a linear free resolution more specifically, if I take just I'll just write things. I won't say anything for a little bit. And before I moved in, I asked a neighbor, is the train an issue? And the neighbor said, oh, well, it's fine. They only come on weekends. Don't know what they were thinking of. Well, so this is the familiar Koszul complex. This thing is expressible in the notation that I've introduced above as R and then join a set of variables x sub 1, 1. So in this case, x sub 1, 1 is just two Koszul variables mapping to the two algebra generators of my ring. And provided that my ring is standard graded, which I guess I didn't really mention explicitly, but provided that that's the case, then this will be concentrated on the diagonal, and that corresponds to every entry in this matrix, and this matrix being linear, which is why this is called having a linear free resolution. So that's what happens if all of your deviations are concentrated on the diagonal entirely, but what if you only have most of them concentrated on the diagonal? And Avramov and Piva proved back in 2002 that in such a situation, so if you have off diagonal vanishing, not for the whole diagonal, but everywhere in homological degree 2 and greater, then R has to break up in this particular way. R is a tensor product of these two rings over the field K, and here Q is a polynomial ring, and S is standard graded Koszul. So a quick example of this, well, I mean, one example would just be to snidely turn back to this example up here and say, well, what if I arbitrarily assigned the degree of y to be 2 instead of 1? In such a circumstance, my ring breaks up into the tensor of R adjoin X and excuse me, K adjoin X and K adjoin Y. And I mean, that would be kind of a snide example. Let me do more of a real example on a new page here. So a more honest example would be like, well, keep it standard graded. The degree of X will still equal the degree of Y and will equal 1. Well, but I guess well, okay. I'll just write this out. Here's my 3 algebra generators. Here's my ring. I'm going to quotient by some stuff. And this breaks apart as just the X's and the Y's, tensored over the residue field with the Z. And here's my polynomial ring that's not standard graded. Here's my standard graded Koszul ring. And you can check that the deviations of this ring satisfy the property that I described above. The point is that the fact that you adjoin this variable in degree greater than 1 means that whatever relations you would want to mod out by here, those would all force there to be non-trivial off-diagonal deviations in higher homological degrees. So the assumption on the deviations forces that you can't have any relations involving these algebra generators. Of course, we can push this past one more level. We can not just assume that the diagonal, we can assume that the off-diagonal deviations vanish in homological degrees 3 and higher instead of 2 and higher. Remember that vanishing of the deviations, just all of the deviations, none of this diagonal stuff, but deviations vanishing in 2 and higher, that was associated with regularity, and so is associated with this polynomial ring piece. So since vanishing of deviations in degree 3 and higher was associated with being a complete intersection, one might conjecture, as Ferraro did back in 2018, that the off-diagonal deviations vanish for homological degrees 3 and higher. Maybe this polynomial ring will turn into a complete intersection. That's what he conjectured. So Q is now a complete intersection instead of a Koszul ring, and S is now going to be standard graded Koszul again. For an example of what this looks like, well, I can just take my example from before. R adjoining 3 variables. But now I'm going to mod out by something on the Z side of things, but it's not going to tie the Z up with the X and Y. That's the key point here. And that's going to allow me to break this up to a tensor product again. KZ mod Z cubed. And this piece over here is a complete intersection. So if you actually analyze the deviations of this thing, you can put them into a little table. Looking something like this. So let's see here. I'll put down 4 homological degrees worth of deviations, and then here's the internal degree of those deviations. Oop, probably a little bit too narrow of a column there. And let's see here. This will be 2 because x and y were degree 1. And then this one right here will be 1 because z had internal degree 2. And then I'll get some diagonal deviations coming from the Koszul piece of this tensor product. And then, well, if I resolve K over this ring, the way that I would build the resolution is by adjoining some variable mapping to this cycle z squared times e in the Koszul complex on the variable z. That's how I would resolve K over this ring right here. This thing has degree, it's going to be 3 times the degree of z. So I guess this thing would actually be degree 6, which puts me outside of the table, way down here. I'd have to adjoin one variable in that homological degree, but there's nothing else in this table off the diagonal. Everything else just goes on the diagonal forever down here. So that's the idea behind this conjecture, that all rings whose table looks something like this, with this diagonal property, they all ought to break up in the manner that's analogous to how they broke up for the Avramov and Piva theorem. So I came up with a counterexample to this, and I should talk about that for a little bit. I was trying to prove it for a while. I kind of banged my head against a wall for a while on it. And then I decided, you know, I'm just going to look through like a big list of Koszul rings, and I'm just going to try and find something, and just try and get something to work. And pretty much the first ring that I picked, I ended up managing to get something out of. And here's how I did it. In the back of my mind, I had this theorem, which Jack Shamish proved back in '69. And it allows you to relate the deviations of a quotient by a regular element. So if I have some other ring R prime, and I express my ring of interest R as a quotient of R prime by some polynomial f, for f non-zero divisor. So this is going to be a degree J polynomial, and I need J to be at least 2. I need that to be at least 2 because I don't want to be modding out by like a variable or a linear span of variables. And you'll see why when I write down this expression right here. The deviations of R are related to the deviations of R prime by the following formula. They'll go up by 1 in homological degree 2 and in internal degree J, the degree of F. And they will, oh, I guess I shouldn't have written, yeah, I shouldn't have assigned J this value because I'm now using it as like a variable later on, a varying index later on. Sorry about that. Right, so it's exactly the same everywhere except in homological degree 2 and in internal degree matching the internal degree of the thing you modded out by. And this is why I needed that degree to be at least 2, because if I modded out by a variable, that would have dropped the deviation in homological degree 1 instead of in homological degree 2. Instead of increasing it in homological degree 2. That's the role of that degree right there. Well, based on this theorem, the idea is take a small Koszul ring that's easy to understand, easy to get your hands on, and just mod out by an element of degree 3, by a regular element. degree 3. And by this theorem above, such a ring, such a choice of R will satisfy the deviation property. Satisfy the hypothesis of the conjecture. Armed with this knowledge, I went to this big list. There's this paper that Roos published that just has this big list of rings, many of which are Koszul. Like, and he says which one of them are Koszul and which ones aren't. So you just go through that list, find one that has depth at least 1 so that you can pick a regular element to mod out by, and then mod out by it and try it out. And basically the first ring that I tried ended up producing this counterexample. So the example is R equals K adjoin XYZ. This is standard graded. And then I'll quotient by, oh, sorry, this is actually R prime, because I need to mod out by a regular element after the fact. So this thing is Koszul. It has a linear free resolution, and it's Cohen-Macaulay with depth 1. I'm going to take, well, I can do this with any homogeneous non-zero divisor of degree 3, but I'm going to do this for a particular one just to make it a little bit more concrete. One that works is x cubed plus y cubed. This choice of f works. This is a non-zero divisor. The Hilbert series of this thing of R equals R mod f. Its Hilbert series is 1 plus t cubed times 1 plus 2t. And this is where it's nice that it was Cohen-Macaulay, because now its Hilbert series is just a Hilbert polynomial, since this is a dimension 0 ring now. Well, if I'm able to express this R as a tensor product over K with of these two rings A and B, just full stop, just any A and B, not just you know, a complete intersection and a Koszul ring, but just any tensor product at all. Well, any chain of primes in either of these factors could be lifted to a chain of primes in this tensor product. So, whoops, I should have said A and B. Well, I've been doing commutative algebra so long that my and has become a tensor product symbol. Well, these both have to have dimension 0, which means that their Hilbert series are also Hilbert polynomials. The other thing about Hilbert series is that if you take a tensor product over K, the K vector spaces dimensions of each graded piece add together according to, like, you multiply the generating functions together. That's what you do to relate these two together. So that combined with the fact that these have to have dimension 0, that means that they have to be polynomials. The Hilbert series of A and B are polynomials dividing this polynomial up here. Well, if I want both of these to be non-trivial rings, like I don't want one of them to be a copy of K or something like that, I need I need one of these factors to go with A, one of them to go with B. So I'm just going to focus on this factor right now. Well, the issue here is that only one ring has this as its Hilbert function. And that one ring is just like a K adjoin, two variables, S and T, and mod out by the square of the maximal ideal. Whoops. S squared, ST, T squared. From this, I can conclude that back in R, there exist two elements, G1 and G2, which square to 0 and are linearly independent. These elements are just going to be the lifts of S and T to this tensor product up here. Those are certainly linearly independent, and they square to 0 because of this relation down here. Well, now all I need to do is go back to my ring. I mean, this was some concrete example, right? I actually modded out by some relations up here. I can actually ask myself, is there a pair of such elements? And it turns out that there is not. So just, let A, oh, sorry, these are not just any elements, but they're also degree 1 elements. I should have mentioned that fact because the S and T are degree 1 because of the 2T right here. Oh, I guess I shouldn't have used T. I just realized that. That was a bit of a boo-boo, but hopefully you all know what I mean. Just overuse of a variable name. So if I just take some arbitrary element, arbitrary linear element, x plus by plus cz, and I set it square equal to 0, you do some calculations that anyone could do following their nose, blah, 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 and conclude that A must equal 0 and B must equal 0. So any elements that square to 0 must belong to the K-span of just this one-dimensional vector space. So that results in a contradiction. There's just not enough room. That's the problem. There isn't enough room in this ring for it to break into the two pieces that we needed to break into. Well, I thought about this counterexample for a little bit, and it's a very particular counterexample. It was constructed, just scrolling all the way back up here. I used this theorem from Shamish. I started with a Koszul ring. I modded out by some stuff. I mean, I guess extending things a little bit, like I could always mod out by more than just one element. Like I could start with maybe take my counterexample, join another variable to it so that it's step 2, and then mod out by 2 regular elements of degree 3, something like that. I could just kind of stack it bigger and bigger. So I thought, well, this is this whole family of counterexamples. Is there some other family of counterexamples? And what I ended up proving was that this is exactly the only type of counterexample that could possibly exist. Namely, I proved that if you have this non-vanishing, I always say this backwards, if you have this vanishing property on the deviations, non-vanishing property. So if epsilon ij of r is equal to 0 off the diagonal for I at least 3, then it breaks up into this tensor product, but you have to mod out by a regular sequence potentially. That's the unfortunate reality that we're confronted with based on that counterexample above. And S is going to be standard graded Koszul. And F is a regular sequence. And Q has to be a polynomial ring. potentially non-standard graded. Just like the earlier example that we saw applying the Avramov and Piva theme. So before I say just a couple of comments about the proof, I won't go too much into details about it, but I will just mention a few key points. But I already kind of talked about this, but I just want to write it down for posterity. So this shows that the counterexample I found is the only type of counterexample. And the other thing that I wanted to mention is that, I mean, this looks very similar, right? This is very similar to Ferraro's original conjecture. The only difference is that you can't take this piece right here and shove it all over onto the polynomial ring. You can't get that, you can't get the tensor product to split up over the quotient like that. So that's my second remark. It's very similar. Whoop. Very similar. It's essentially just that, I mean, this is kind of abusing notation, but my regular sequence is not contained in Q. This is really what's going on. It might tie them together in some non-trivial way. So, like I said, I was going to say just a couple of remarks about the proof of this thing. You write your ring as a quotient of a polynomial ring. And I don't want any silly presentation of R. I want to take one where the degrees are in decreasing order and they are at least 2. I don't want to mod out by like a linear span of the variables or something like that. And then I have that the number of these f's of a particular degree, this is the same thing as that second deviation, but in degree j in particular. So if all these f's are of degree 2, we're done by the Avramov and Piva result. So this suggests that we're done in such a circumstance because then we can just say, well, it breaks up as a tensor product of a polynomial ring and a Koszul ring already. We don't even need to mod out by a regular sequence or anything like that. So this suggests some kind of induction. We're going to induct on the number of elements of degree bigger than 2. And the way that you set up the induction is you examine the long exact sequence in Koszul homology that you get by considering multiplying by F1. Fitting in here is the kernel right there. And the third deviation of the ring is supposed to be identifying a minimal generating set of this. That's something that one can show about the deviations and how they relate to the relations of the ideal, the f's. So you can do some type of degree counting argument and use Nakayama's lemma to conclude that. So degree counting plus Nakayama to conclude that this capital N has to just be 0. And now you apply that Shamash theorem from earlier to say, well, we mod it out by a regular element F1, take that off. Now we have a new ring that has a fewer number of degree greater than 3 relations and still has that same vanishing property on its deviations. So you imply induction. And let's see here. I want to say this. No, I think I'll just skip to rigidity. So that's all I have to say about this idea of like vanishing of deviations and what the implications are for the ring theoretic properties of R. So this is why one would be interested in this type of off-diagonal vanishing property. It tells you something about the structure of the ring in this particular fashion. Now, one important result, I guess I didn't number my other sections, so I guess I should just say rigidity. There's this important result that characterizes the rigidity properties of deviations in the ungraded case, in the local case. It says that R is a complete intersection, and this part was proven by Gullickson in 71. That the deviations vanish eventually. And Gullickson later proved that R is a complete intersection if and only if the deviations vanish eventually, but for even indices. So I'll punch that in here. And the most strong form of this was proven by Halperin in 87, that if even a single deviation vanishes, for I greater than, for I greater than 0. I guess if the first deviation vanished, you would just be working with a field or something like that. So like, silly, but still technically correct, which is the best kind of correct. So what this is telling us is that there's like a huge gap in the homological behavior of complete intersections and non-complete intersections. If you're a complete intersection, you adjoin finitely many of these variables to resolve K. If you are not a complete intersection, not only do you have to adjoin infinitely many of these, but you end up having to adjoin variables in literally every single homological degree going all the way out to infinity. So it's this very strong statement about how fast the resolution of K over R must grow. All right, so
I think Josh is suggesting in the chat that you might want to quantify you. So for some I greater than 0.
Oh, right, yeah, for some I. Thank you. There exists an I greater than 0 for which the deviation vanishes. Yeah, I guess otherwise you would read it as for all I, probably would be the more natural reading. So good catch. So motivated by all of these results up here, and also by the decomposition about like CIs and stuff, you might think, well, maybe we can prove something like this for off-diagonal deviations. So this is something that Ferraro also conjectured back in 2018. He conjectured that if these off-diagonal deviations vanish eventually, then they must do so immediately. And this is something that is interesting to think about, even if you are not really interested in all this GG algebra stuff, because you can make conclusions about the structure of the Betti numbers, the growth of the off-diagonal Betti numbers. So that's like a growth in the complexity of the polynomials appearing in the matrices of the differentials, something like that. And there was some partial work on this. Namely that if you have eventual vanishing past D, then, and if D is even, then you have to have vanishing off the diagonal. Sorry, I forgot to say that this equals 0. Vanishing off the diagonal for I not equal to J and I greater than or equal to D minus 1. So you can push it just one lower. So like if you're, what you really need to be concerned about is like the possibility that your odd deviations don't vanish. That's the idea here. And I was able to extend this quite a bit. I ended up getting something similar to the theorem that Gullickson proved back in the 80s about the even deviations vanishing. Like if all your even deviations vanish, then you're good, is kind of the idea. So it's that if you have this off-diagonal vanishing for I not equal to J, and this happens eventually, then it must happen for all I not equal to J and all odd I greater than or equal to 3. And I'm starting to run a little bit low on time here, so I'm probably not going to say very much about this proof, except that basically what I did, it honestly wasn't super impressive. What I did is you look at Halperin's proof and you decorate everything with degrees. This is Halperin's proof for this result up here, that vanishing of even a single deviation suffices. You look at that proof and you just put degrees everywhere. And you are in good shape, provided that the homological degree in question is odd. If the homological degree in question is odd, then everything goes through and you get this contradiction, and so you get that the odd deviations all have to vanish. When things are even, things unfortunately break down. You can't use exactly the same technique. So you use Halperin's proof to show this, which works in the odd case only, essentially, is what's going on here. All right, and then just to wrap things up, I have a few general remarks. Well, I guess maybe just one remark to finish things off. The two theorems discussed above about rigidity of deviations and the vanishing of deviations and their consequences for the structure of the ring. There's also a way to do all of this stuff with deviations in like the relative case, so not just for a ring, but for a map between rings. And it's more complicated to explain and describe, which is why I didn't present it in this fashion. But suitably interpreted, everything above just works in the relative case with essentially no modification. So probably good to record this as a fact. And with that, I think I will call it.
Let's thank Michael. Questions for Michael? So looking at Gullickson's results up above, right, there are questions. So you've hinted at one already, right? What happens for the odd homological degrees, but there's also the question, right? You have to assume sufficiently large vanishing in order to get your even vanishing. What if you just have one vanishing?
Right. Yeah. So one way to interpret this is as soon as you have an odd deviation that does not vanish, and it does not vanish for some homological degree greater than 3 or equal to 3, then, well, I guess maybe I should have just really what this statement is, probably should have written it this way. Yeah, I'll just write it down here. Really, the statement is if you have a non-vanishing deviation off the diagonal and it's in some odd position and it is greater than or equal to 3, then epsilon I plus t j plus, well, this is kind of technical. For each t in. So it's like once you have a non-vanishing off-diagonal deviation, you look at that gap, and that gap just like grows outwards. It never shrinks. You have an off-diagonal deviation in higher homological degree that's at least as far away from the diagonal, and it's in every single subsequent degree. So it's very similar. It's just that it only works in one case. If it worked in both cases, you really would have something kind of more akin to the Halperin result, where it's like as soon as you have non-vanishing deviations, they must do so immediately.
Other questions? All right, let's thank Michael again.